So this is an experiment to look at how current compares to voltage across a resistor, and then we're going to add a capacitor. And so we have to use the LabQuest stream and the analog current and voltage probes. And you need to select, so plugging the LabQuest via USB into the computer, and you can get 10,000 hertz. The reason we can't use the go direct is the digital rather than analog, and you can only get 1,000 hertz out of that, and that's insufficient. So now with the differential voltage probe connected across the light bulb, we can click done, and then have current and voltage plotted at the same time, and click collect. Takes a little bit of time to do that, and we're running at 4 volts AC. Because we're using the differential voltage probe, it maxes out at 6 volts, and so we have to have less than 6 volts peak, and you can already see on the graph that it's already maxed out. And we can see they're 180 degrees out of phase, which may seem at first instance a bit confusing, but if we just switch the voltmeter around, then we click collect a second time, and we should get a graph where when the voltage is high, the current is high; when the voltage is low, the current is low, and so forth. And that's pretty easy. That's quite a good little learning curve. V equals IR, they're all the same. And now what we're going to do is we're going to add a capacitor in the circuit. So this is running 4 volts AC with a 12 volt bulb, and now I'm going to add a 32 microfarad capacitor. With the voltmeter still across the resistor, we still expect to see something similar. With the voltage and current being in phase. That's great. What we're going to do now is move the voltmeter across the capacitor instead of being across the resistor. So now the voltmeter is across the capacitor. We hit collect again, and now we would expect the voltage to lag the current by 90 degrees. That's really hard to see, and so if we come over to the side and we click current and we go new calculated column, and then I go insert expression and AX times B, and if I just times the current by 30, then it's just making it easier to see. So I times 30 and click apply, and instead of plotting a current graph, I can plot an I times 30 graph, and we can see that the voltage lags the current. So voltage is there and the current is there, and so the voltage lags the current by 90 degrees, which is good. So if we go to our phasor diagram, I say when you go to the toilet you go for a crap, and so that goes down, you roll along, and if you love, you're putting your hands up, it's all positives and fluffies. And so when C is down, you should get I being 0, and so that is what we see. When VC is there, I get an I of 0, and as I phase up as I turn that phasor around, it is perfectly out by 90 degrees, so that's awesome. If we now go back to that initial circuit where it's just an ammeter, a bulb, and the power supply, then we can do a calculated column for power. And so instead of I times 30, I can just go I. Again, that's quite small. If I wanted to add a calculated column, so I'm going to call this calculated column power, and then insert expression, and then it'll be X times Y, and so it's going to be potential difference or voltage times current, so that's what power is. And then if I turn that on, then I get this beautiful power graph, and I can hit collect again and collect that same data, but we're seeing that the power data is always positive, and so you can see how many watts you're getting there, which is quite nice.